So we are starting a new unit. Yeah, this is probably the longest title for a unit the whole year, but whatever. We are going to look at more exponential and logarithmic functions, and then we're going to deal with differential equations. We're going to spend like the first 40 minutes today on the more exponential and logarithmic functions part. The rest of the unit will be looking at those differential equations. One of the 6 free response questions on the AP exam will involve the differential equation piece. I don't really think this is a big deal, but we learn this stuff. So I really just have a whole bunch of different things we need to take care of today. The very first thing we're going to do is actually kind of spread through a bunch of different sections in the book. So I'm not even going to bother giving a section number. We're going to look at something called logarithmic differentiation. Spend maybe 10 minutes on this, and then move into other things. Logarithmic differentiation. For example, let's say y equals x raised to the 2x. We want to find the derivative. So hold on 1 minute. I'm going to do this. I'm going to do that. I want to find the derivative of that thing. Let me tell you 2 things we're not allowed to do. We are not allowed to pull down the power and subtract 1 from the power. That rule works if the power is a constant, not if the power is a variable. We're also not allowed to use the rule that says, well, the derivative of e raised to any power is just e to that thing times the other thing. Why can't we use that rule? It's not e, and in fact, we will deal with later today how to deal with like 2 raised to the x or 3 raised to the x, but this is a variable raised to something. So none of those rules that we already know will work. We need to use this new method called logarithmic differentiation. Here's how this works. The first thing we're going to do is we're going to take the natural log of both sides. Take the ln of both sides. I think I'll add more to that in just a moment, but I'm going to say the natural log of y equals the natural log of x raised to 2x. So I think I actually made it look even worse. What's the point? Kaylee? Sure. Because we took the natural log of both sides, now our natural log properties apply, so I can take that 2x and I can move it out front. So I'm going to say the natural log of y equals 2x times the natural log of y. So I'm actually going to change the direction to take the natural log of both sides and simplify. That's really the whole point of taking the natural log of both sides. Step number 2, we're going to go find the derivative. Now, can we handle finding the derivative if it's ln of y rather than just y? What do we have to use? Yeah, what's that called? Implicit differentiation. Deal with x normally, deal with y by getting those dy dx things. So step number 2 is going to be differentiate implicitly. Differentiate implicitly. So I want to find the derivative of the left side, the natural log of y, and I want to find the derivative of the right side. I think you know how to do this. Take a moment right now, go find the derivative of both sides. So I'm getting 1 over y dy dx equals 2 plus 2 ln of x. Okay, bless you. I'm not done, I guess, with the implicit part. What should I do next? Gotta be louder. Multiply both sides by y, sure. So we're going to say dy dx equals, I'm just going to kind of leave it out front. I'm going to say y times 2 plus 2 ln of x. Does this look okay for a final answer? Arthur, what's my problem with this? Yeah, we could factor out a 2, but I've got a bigger issue. There's a y. The original thing was an explicit function, y equals something with just x's, so the derivative should be something with just x's as well. So what can we do? We know what y is. Y is just x raised to the 2x. Why don't we just plug that in? I'm going to say step number 3. We already kind of started step number 3, I guess. Solve for dy dx and give the answer just in terms of x. Which means we're just going to replace that y that we have with x equals, not x equals, with y equals x raised to the 2x. So I'm going to say dy dx equals x to the 2x times 2 plus 2 ln of x. And that is my derivative. So no, we're not really going to have like a formula for how to do the derivative of x raised to the x or something like that. We're going to use this process instead. Take the natural log of both sides and simplify. Go do your derivative implicitly, so you'll get a 1 over y dy dx. Solve for y, plug in what y is. Questions so far? By the way, what's the point of that thing? What did we just find? The slope. A formula that gives us the slope of that x raised to the 2x. Anyway. Nod your head if you're with me. You think you can do one on your own? Well, some of you are going to try, others of you are going to wait, and we'll deal with those things together in a moment. Let's take a look at, let's try this one. Y equals the sine of 3x. And I want to raise that whole thing to the x squared minus 2. Take a few moments, see if you can find the derivative. None of our derivative rules will work because variables in both the base and the power, so we need to use this logarithmic differentiation. Try it. Hopefully we started out with something like that. I haven't done any calculus yet, just the natural log stuff and the properties. Okay, take a look at my derivative line. I've got a lot of cleaning up to do. Realize that with the natural log of the sine of 3x, that's a 3-part chain rule problem. Deal with the natural log, deal with your sine, deal with your 3x. And also definitely realize that I'm using product rule on this thing. Questions? No, you don't need to. I just figured that would look nicer than a cosine over a sine. Less writing. In general, these derivatives are not going to look terribly pretty. That's just kind of the nature of these things. Again, the whole point of this is we're finding a formula. That's going to give us the slope of the original thing. Problem? Yeah. These are not necessarily going to look terribly pretty. It's okay. Questions on pieces of this? So in general, can you review? Thank you. In general, you're not going to be told things like, use logarithmic differentiation to find the derivative of this thing. You're just going to need to kind of know when to use it. What did I already say was kind of the case where we have to use this method? What in the problem would kind of tell us, Kaylee? Well, but we've already seen things where the power has a variable like e to the x, and that was okay. And we'll actually learn in a moment about 2 to the x, 5 to the x. Those will be okay. We've seen plenty of things with aha. So variables in the base and the power is kind of the signal to us that we need to use logarithmic differentiation to find our derivative. We are going to use this method, use logarithmic differentiation. Oh my goodness. Use logarithmic differentiation when the base and power include variables. You just noticed that? It's been there since October.
Everybody else notice that?
Yeah.
There's one right there. I knew there's one right there. I know over here.
Okay, blow your nose and come back. Are there...
Oh, do we get extra credit for finding?
No. Are there any questions on how this worked? Hannah, you look a little confused. Where did I start to lose you? Ah, okay. So you have everything else, though?
Yeah.
Okay. Other questions from anyone?
Why is this so much?
Because we're adding in those natural logs, because we're using product rule and chain rule inside there, because then we're solving for y. Because actually, in general, the original function is not a terribly simple type of function to deal with. How would you graph that thing? I have no clue. Type that in your calculator. It's going to be a mess.
Would you want us to pull sine of 3x out, and then it would be sine 3x to x squared?
Okay, well, we can't.
That wouldn't.
This one has a sign in the denominator. This is not a sine 3x. This is a natural log of the sine of 3x. It's inside. No. Just leave things. Quasi.
Are we ever going to have to use bullshit rule?
I suppose. No, wait a minute. No, you wouldn't have to, because if there was a quotient inside your natural log, couldn't you just separate it into two different subtraction problems?
Yeah.
Right. So on a scale of 1 to 10 of how important this is as far as things moving forward in here and the AP exam, this is probably a 1 or a 2. This is not a big deal. I will actually be pretty surprised if you do see a question involving this on the AP exam, There is a reason we did this. You'll see why in like 10 minutes. You're going to have like 3 or 4 of these in the homework and 1 on a quiz, and that's really it. This is not a big deal. This is not super important. Next. Okay. So the next thing we need to deal with. We're going to start moving into section 5.5, which also in the grand scheme of things is not one of the more important things. The differential equations part of this unit is a big deal, is important for the AP exam, is important for future math classes. This next topic is not, but we have to do it, so we're going to take care of this. But before we move into section 5.5 for real, we have some pre-calc review to deal with. So 5.5 is all about other exponential functions and other logarithmic functions. We need to first do a little bit of pre-calc review. Oh my God. You know what? Don't call it that then. Call it algebra 2 review, because that's what it is.
I like algebra 2. I took pre-calc on steroids. Huh? Yeah, because my class started.
All right. So, I want to get through this quickly, because you already know this stuff.
From 6
So,
p.m. to like 11:30 p.m.
So, now that Quezzy's done explaining how he did pre-calc, exponential and logarithmic functions. Exponential functions are functions in the form f of x equals a raised to the x, where the base does not include variables, but just some sort of number. 2 to the x, 10 to the x, 1/2 to the x. You learned how to graph those things in algebra 2. It was not, like, necessarily fun. They were kind of painful to graph, but you made tables of values, all that stuff. Logarithmic functions are inverses of those things. Y equals log base 2 of x, y equals log base 10 of x, y equals log base 1/2 of x, and things like that. They're inverses, they undo each other. You've got a graph of y equals 2 to the x, you've got a graph of y equals log base 2 to the x, log base 2 of x. I can figure out the points on this thing by, I can figure out the points on this thing by just making my table of values. I can get the points on the inverse by just switching my x's and y's and plotting them. And the horizontal asymptote, y equals something, becomes a vertical asymptote, x equals something, we're switching the x's and the y's and all that stuff. You do not need to deal with any graphing. What I do need you to realize, though, is all exponential functions will have the same basic shape as e to the x, and all logarithmic functions will have the same basic shape as y equals the natural log of x. That's all we need to deal with there. Next page. Properties of these things. So the first property is sort of our inverse property, kind of our definition of logs. Y equals a to the x is the same thing as x equals log base a of y. As far as like actually thinking about these things, though, I don't really use the inverse properties. The language that I use in algebra 2 is logarithms are all about asking the question, what's the power? So we have the problem 2 to the third equals 8. The related logarithm is log base 2 of 8, which happens to equal 3 by our inverse properties. But what log base 2 of 8 is really asking is 2 raised to what power gives you 8? And the answer is 3. Next, I'm giving you the exponential problem, 81 to the negative 1/2 equals 1/9, because that means move it to the bottom and do the square root and all that stuff. The related log problem is log base 81 of 1/9 equals, well, that's asking 81 to what power gives you 1/9. I know it needs to be a negative power to move it to the bottom of a fraction. I know the square root of 81 is 9, so I'm going to make it a negative 1/2. Do you get what I mean by the logs ask the question, what's the power thing? So you're going to figure out some logs. But did I mess up in the first one and forget to give you a base?
No.
What does it mean if there is no base? 10. Base 10. We call that the common logarithm. There's no base, it's base 10. Take a moment, figure those out by asking yourself, what's the power? And you will have some of these in the homework. These should not take a long time. And I don't see anyone using a calculator, but these things you should be able to do without a calculator. calculator stuff in a moment. Aoife, what do you have for number 1? 2. It's asking us 10 to what power gives you 100? Answer is 2. Sabrina Weiner, how about 2? Also 2. 4 to what power gives us 16? 2. Sanjana, how about 3? 3. 5 to what power gives us 125? 3. Victoria, how about 4? 1. 9 to what power gives us 9? It's 1. And Hannah, how about 5? 0. 8 to what power gives 1? 0. Manoj, how about 6? Negative 3. Negative because we need to move to the bottom of a fraction. 2 to what power gives you 8? Well, 3. So we're going to make this negative 3. Jason, how about 7? Negative 1. Move it to the bottom of a fraction, and then 3 to the first gives us 3. Richie, how about 8? 1/2. Why? Square root. Square root of 9 is 3, so it's a 1/2 power over there. Eva, how about 9? 1/4, because we're doing a 4th root there. And Julia, how about 10? Negative 1/2. Negative because we're moving it to the bottom of a fraction. 1/2 because we're taking a square root. You've been doing this since Algebra 2. This shouldn't be a big deal. Thank you, Don. Number 2, inverse properties. Just like e to the x and the natural log of x are inverses, a to the x and log base a of x are inverses. We can use those to solve equations. We'll deal with those in a little bit. Third thing is we have that change of base formula that you've been using since Algebra 2. Log base a of x equals, we can write any log in terms of a division problem with logs of any other base. So this is log base b of x over log base b of a. But I think the base we're probably going to want to use most often is the natural log, because we actually know things about the natural log. We don't really know calculus applied to other types of logs. So to figure out log base a of x, we can do the natural log of x divided by the natural log of a. Do those things look familiar to you? So you could use just log base 10, I guess. So for example number 3, I evaluated this on my calculator by doing natural log of 15 divided by natural log of 8. The way you probably learned in Algebra 2, and I would assume probably also used in pre-calc, was using log base 10. Log base 10 of 15 divided by log base 10 of 8, and you'll get the exact same thing. And honestly, if your calculator had any other types of log buttons, if it had a log base 2 button, it doesn't. But if it did, you could use log base 2, or log base 17, or log base anything. Turn the page. So I want to solve this first equation, 5 raised to the x minus 3 equals 3,125. If we are using our inverse properties, what is the inverse of a 5 raised to the? What function undoes a 5 raised to the something? Log, what log? Log base 5. So technically, if we're using our inverse properties, I would take the log base 5 of both sides. I'll show you how you probably did this in Algebra 2 and pre-calc in a moment. But if we're going to be formal about this, we're going to do the log base 5 of both sides. Equals this thing. Well, what are we allowed to do on the left side? I've got a power inside a log. By the way, all of our properties of natural logs apply to other logs as well. Move it out front. X minus 3 times log base 5 of 5 equals log base 5 of 3,125. What is log base 5 of 5? 1. So really, this is just saying x minus 3 equals log base 5 of 3,125. The way you probably would have done this in Algebra 2, and I'd assume pre-calc as well, is this thing is in exponential form. I'm going to go and rewrite this thing in log form. Log base 5 of 3,125 equals x minus 3. It's the same thing. I was just kind of trying to show you why we're allowed to do that. You had that?
Yeah, I started with that and then I got some.
Yeah. No, I'm just trying to show you how these are really using inverse properties. I don't really care, though, how you do it. Now I think you're going to need to go to the calculator, because I don't know 5 raised to what power gives me 3,125. Maybe some of you do know. Maybe some of you typed it in the calculator. In general, don't expect nice numbers. They will be decimals, so you'll have to use the calculator. But go to the calculator and use your change base formula. I think it actually is a nice number. And we should get x equals 8. The next one, what would undo a log base 3? Doing what to both sides? 3 raised to the, what you have on both sides. Using your inverse properties will work that way. If you don't really like that and just want to do the it's in log form, put it in exponential form, fine with me, you'll end up in the same place. Take a moment, go solve this one, then we're done with our pre-calc review. And I'm getting 43. It's not. The beginning of your homework will be a little bit of, no, not the beginning. The very beginning of the homework is the logarithmic differentiation. Then you'll have a few pre-calc things evaluating some logs, and then some equations like these that you're going to solve. That shouldn't be a big deal. The new stuff. We need to get into derivatives and integrals involving other logs and other exponential functions. So in your book, this matches up with section 5.5. Other, exponential, and logarithmic functions.
How do you do that symbol thing?
Hold on a moment. I'm pretty sure we talked about this before. First of all, we know what that means, right?
Yeah,
Section. Section 5. Really? We got through the whole year and didn't know? Okay, so that symbol means section. And now F block knows that as well, because they're listening. You make an S. You make another S. Section. You're honestly that impressed by that?
Yes.
Well, you learned something new today.
It looks like the Sims like currency.
Who?
The Sims currency and the game Sims.
Okay. Sure. Okay. So, we're going to start with other logs. The derivative of log base a of x. Well, we don't really know anything about derivatives of logs in general. There is one log, though, you do know how to deal with. Natural logs. Well, is there any way to rewrite this problem in terms of natural logs? Hannah? Change base formula. This is the same thing as saying, let's do the derivative of the natural log of x divided by the natural log of a, which is the same thing as saying, let's do the derivative of 1 over the natural log of a times the natural log of x. Couldn't I just split up my fraction like that? 1 over the natural log of a. What is that? Just a constant. So I don't need quotient rule on this thing, and now I don't need product rule. This thing is just a constant. I'm just going to leave that alone. I'm going to get, well, my constant multiplier rule says I'm just going to leave that constant multiplier out front, and I'm just going to multiply by the derivative of the natural log of x. 1 over x. So I actually have my formula. The derivative of log base a of x is 1 over the natural log of a times 1 over x. We're going to get a total of 3 formulas, by the way, today. At the end of class, I'll try to end early, pass out index cards, and we'll get them all on there. Oh, no. Okay, so we're not going to do that. So first, hopefully pretty easy example. We're going to take a look at y equals log base 5 of x. There's nothing fancy or anything that I need to do here. I'm just going to use my new rule exactly the way it's written. And I'm going to get a derivative of 1 over the natural log of 5 times 1 over x. Which I guess we could clean up if we want. We could say 1 over x ln of 5. I'd be fine with either. And again, what's the point of this? What are we finding? Slope. That formula gives us the slope of our log base 5 of x. What I kind of need you to realize is this is really just another new derivative formula. Everything you already know, product rule, quotient rule, chain rule, can be applied to this thing. Anytime we have a log base something of something else, we use this new formula, basically. So I would like you to take a moment and find the derivative of y equals log base 4 of 2x minus 3. I'm looking at this and I'm seeing chain rule. I'm seeing first deal with that log base 4 and all that stuff, and then deal with the stuff inside. Good? Now what? Times 2. I'm honestly fine if you leave it in this kind of expanded multiplication form, but if you want to try to make it look a little prettier, maybe 2 over... Good? I've got an issue with writing it like this, and I will take off if you write it like this. We need parentheses. Yeah, 2 over 2x minus 3 times 1 over ln 4. Any of those versions would be okay. Right, because otherwise you're really saying just multiply the negative 3 times the natural log, and that's not what we want. Any issues so far? Anyone? Okay. I think we only need to do one more of these. Y equals log base 3 of the square root of x minus 1. You know, I feel like I could make this easier. To the 1/2, which then, this is, log base 3 is like any type of log. We can use our properties that say we can rewrite our original problem as a half times log base 3 of x minus 1. Properties of natural logs apply to other logs as well. If you can use those properties, use them to make it nicer. Now go do your derivative. This is really not a big deal, I don't think. Just find your derivative. Maybe something like that. And also the x minus 1? Yeah. Then you're fine. Questions on this? Don't expect these to get terribly complicated. As I think I already mentioned, this is not a big topic on the AP exam. More likely to see this than the logarithmic differentiation stuff, but it's not a big deal. It doesn't really go anywhere. We just need to learn these formulas. And really, they are just more formulas. Okay, so other exponential functions. Other exponential functions. By the way, with our other logs, I didn't teach you how to do the integral of natural log of x, right? No, I didn't. I will in like April or May. It's not on the AP exam. It's something else. Oh my gosh. Okay, stop. Similarly, we're not going to bother with integrals of other types of logs for the same reason that, well, we'll deal with that later. Exponential functions, the derivative of a raised to the x, so some constant raised to the x. Well, here's what I'm going to do. I'm going to say, instead of doing this problem, why don't I say y equals a to the x and find y prime. It's the same thing, just written in a different notation. So I want to figure out how to do the derivative of this thing. I want to create my formula here. You don't know how to do the derivative of a constant raised to a variable unless the constant was e. Is there anything we could do to help us do something with this? Nathan, you've got the right idea, flipping back a page. Why don't we try that to maybe use that to create our formula? What was that? We're going to use it to create our formula for the derivative of the x. Oh my goodness. So I'm going to use logarithmic differentiation. I'm going to take the natural log of both sides. Natural log of y equals the natural log of a raised to the x. That's why we did the beginning of today. What's the point of this? What can I do? Move the x out front. Natural log of y equals x times the natural log of a. And I'm going to go and find my derivative of this thing. Okay, derivative of the natural log of y. Easy, I hope. 1 over y dy dx, sure, dy dx over y. I'm going to say 1 over y dy dx. Do I need the product rule on the right side? Why not? It's a product. Good. Natural log of a is just a constant. So actually, the right side is just x times a constant. It's just the constant, right? Derivative of x is just 1. So isn't this side just the natural log of a? So the derivative is y times the natural log of a. So the derivative is a raised to the x times the natural log of a. Or to kind of make it fit the same form as our log thing, I'm going to stick the ln piece first. And I'm going to say that the derivative of a raised to the x equals the natural log of a times a to the x. In the log version, I was doing 1 over a natural log. Here I have the natural log of a. I do think that of all of our derivative and integral formulas, these 3 that we're dealing with today are probably the toughest to memorize, only because they look very similar. They'll all involve natural logs of a, but sometimes it's 1 over it, sometimes it's just times. That's going to make this part a little bit tricky. Again, we'll end early, we'll make index cards with these. Or if not, we'll do that next time.
Wait, so is dy dx equal to a to the x natural log of a wrong?
No, I just kind of now want to write this in my normal, okay, here's my formula for the derivative of a raised to the x. Question? Okay, so let's use this. I think you could probably handle this first example. It's really just using the formula. Find the derivative of a raised to the x. No, don't do that. Find the derivative of 4 raised to the x. Do what I wrote, not what I said. Just do the problem. You mean to this? I was creating the formula to show you where it comes from. Now that we have the formula, you're just using the formula. I don't think this one should involve any work at all. Absolutely. That's what I want you to do. I wanted to show you where the formula came from, so it wasn't just, just trust me, here's the formula. But now that we have it, we're just going to use it. Natural log of 4 times 4 to the x, done. Is that okay? I would like you to find the derivative of y equals 5 raised to the 2x cubed minus 4x. It's not. Do the derivative. This looks like chain rule to me, right? Do the derivative of 5 raised to that thing, we have a rule for that, times the derivative of that thing inside. Okay, just do the problem. I'm not going to bother doing anything else. I'm just going to put a box around that, and I'm going to be done. Do you get what I said a little earlier ago about how really these are just more formulas to add to your list of things you already know? All the stuff, chain rule, product rule, quotient rule, all those things still apply. We just now can add other logs into those problems or other exponential functions. I would like you to find the derivative of y equals 6 to the x times x squared. And when you're done, do a little bit of simplifying. You can clean it up a little bit. Of course, you should be thinking of what rule? Product rule. Use it. Maybe a line like that. 6 to the x times 2x plus x squared times the natural log of 6 times 6 to the x. But we can clean it up. Emily, what can I do here? I can. Anything else? 6 to the x. Let's take out an x. Let's take out a 6 to the x. So that'll give us a 2. And looks like an x ln of 6. And I think I would prefer that version, only because we can do a little bit of simplifying here. Absolutely. Any derivative questions? Anyone? Anything? Okay, we're going to move into integrals. You are no longer going to think about things like chain rule, product rule, quotient rule. U substitution is basically our one and only trick we know for integrals. Oh, good. Okay, so integrals. The integral of a to the x dx. I'm just going to give you this formula. 1 over the natural log of a times a to the x plus a constant. We'll talk through that, but we're not going to go through a big, long, drawn-out thing. I'm asking you what has a derivative of a to the x dx. Well, this thing will, because this is just a constant. The derivative of a to the x is the natural log of a times a to the x. Those things cancel, giving you the a to the x piece. That's where it comes from. Take a moment. Find the integral of 3 to the x dx. This should not involve much thinking at all. You have the formula, just plug in and you're done. And absolutely, 3 to the x over ln 3 plus a constant, all good. A little more involved. Let's try the integral of x cubed times 6 x to the 4th minus 2 dx. Do you think you can do this on your own? Do it.